Data Analysis Part 3, Hazards of Overinterpreting Descriptive Statistics, and some comments on numerical statistics. Hello everyone, welcome to Part 3 of this video series summarising the MPhil ACE Data Analysis course. Where we got to at the end of video 2 was looking at this particular question where we have a descriptive statistic. It shows in this map from a literature textbook which you can get from the recommended reading, Gellman's Bayesian Data Analysis. What reason explains this figure where we have a map of the USA, and shaded in black are the counties where the kidney cancer death rate is among the highest 10% of kidney cancer death rates for all counties in the USA. Can we explain how this comes about? It's true, the data is correct, but why does it come about? How can we explain that, and at the same time explain this other map of low kidney cancer death rates? So, shaded in black, counties which have among the lowest 10% of death rates for kidney cancer, measured over some period of time, 1980 to 1989. Okay, this is a good example because it shows very clearly you can imagine how people overinterpret this. So, as it happens, both of these maps look roughly the same. You've got counties in the west of the USA and in the Midwest of the USA, and relatively few counties on the coasts. In both the low death rate and the high death rate examples. So let's start off with high death rate. Well, if you give this to a journalist, they probably immediately start writing you an article, and it says, aha, so there's high kidney cancer death rates among counties in the Midwest and the West, and this is easy to explain. They'll tell you this must come about because, well, these are rural farming counties, and probably they might say, the people who live in these rural farming counties, they're exposed to chemicals, and the chemicals cause them to get kidney cancer. And an advanced journalist might add on top of this another wrong interpretation. They might add that, these are rural counties where people are really stubborn out in the country, and they refuse to go to the doctor, and they don't pay proper attention to the doctor. And probably the doctors who live out in the country don't know what they're doing. All of this leads to bad medical care and late diagnosis, and a higher death rate from kidney cancer. That would be an interpretation of the data. Shortly we'll see why this is an overinterpretation, and it's almost certainly wrong. Because let's consider what would the same overinterpreting journalist give you for the map of counties with low kidney cancer death rates. Well, they'd probably tell you, yes, well, you can see there's low kidney cancer death rates in these counties, mainly in the Midwest and the West, and that's because these are rural counties, and the people in the rural areas benefit from clean, open air and healthy, wholesome outdoor living and activities, and because of this, they're not exposed to the chemicals which they would be exposed to in the big cities on the coast, and hence they're healthy people, and they have low kidney cancer death rates. Oh, on top of that, you've got strong rural stock and good medical common sense, which does them much more good than the pills which are overprescribed by fancy doctors or living on the coasts. Okay, actually, let's look at these explanations are, I think, probably wrong. They're not definitively wrong, but let's now consider what is a better explanation. Well, the better explanation is that both the low kidney cancer death rates in the West and the Midwest, and the high kidney cancer death rates which are in the West and Midwest, these are actually, what we can say is these are in rural counties which are actually quite low population counties. You see, it doesn't happen among the higher population counties on the coasts. And what is probably the best explanation for this? Well, it's simply that kidney cancer is a quite rare disease. And if you have a small population county out somewhere in the west of the USA, it's quite possible there are no cases of kidney cancer in a particular observation period of, say, 10 years. And if there are no cases, then that county is by definition tied for the joint lowest possible, 0, kidney cancer death rate in the USA. Conversely, kidney cancer is a rare disease, but it does happen, and it's quite possible that one of these low population counties might have a case, or even a few cases, but most likely just one case. And if so, one case divided into a population of a couple of thousand still gives that county among the highest 10% kidney cancer death rates in the USA. So meanwhile, in the coastal counties, let's say they have a population of hundreds of thousands, the nature of statistics and probability means that these counties most commonly have a number of actual cases of kidney cancer closer to the average expected number of cases, and they're in the middle, and they don't feature in either the joint lowest 0 number of cases, nor in the unusually high percentage of cases where you have a rural county with one case in 1,000 population, or something like that. So you see how actually it's possible to come up with so-called scientific conclusions to explain data which are actually completely unnecessary. Sometimes the reason for what looks like a pattern in the data is purely down to the way that the data has been acquired. Now, part of this course is we'll want to look at hazards of data analysis, hazards of over-interpreting data or misinterpreting data in some other ways, and we want to make sure that we design experiments to avoid them. Or if we're not doing experiment and we're reading some news, we want to see what mistakes a reporter might have made when they're giving us some data, so that we know whether to possibly distrust or look more deeply into some data, or whether it looks like respectable results which we can safely interpret. That's where we will be going in Chapter 3 and beyond in this course. In Chapter 4, we'll look a bit at probability theory for some of the basis of what I said about higher population counties being more likely to have a death rate closer to the average and not in the extreme 10%. But that's not the main emphasis of this course. Especially for this lecture, we want to look qualitatively at some of the hazards of data analysis and what we need to do to avoid falling into being duped by these hazards. Right. When you are given data to interpret, it might be a nice map, or like the map of the USA we just looked at, but it's very likely to be a table of numbers, and it might be given to you along with some algebraic interpretation. The notes of this course and this course are not mainly a algebraic course. If you do want the notes for an algebraic course on statistics, I will put up on the Moodle site my sampling theory statistics course, which is an undergraduate course. So that looks in great detail at the notation and the proofs for algebraic proper quantities in sampling theory statistics. So in detail, what is a sample mean? What is the difference between a sample mean and a population mean? What is a estimator for some property of a population? Why do certain estimators have nice properties, such as being unbiased or efficient? And what do those terms mean? Now, that's more of an undergraduate maths course, and that sort of maths is best understood by reading. So I will put up the notes for that course on for those of you taking the MPhil ACE, I will put up the notes for that sampling theory statistics course in case you want to follow through some of the algebra. But for the most part, in this course, I just want to make you aware of some important conventions when you get given statistics written as numbers or statistics which use algebraic formulae, I want to go through in this section of the notes, section 2.4, some things that you definitely should be aware of when you're reading numerical statistics in algebra. So I'll present these for an example. So the example is, you imagine someone's done an experiment, and this is section 2.4a. The experiment is described in the caption of the table, as it should be. Increase in corn yields is the experiment. 14 fields in Iowa were divided in two. Half was sprayed with some chemical to treat a pest, and the other half was not sprayed. The increase in yield in some unit for the treated halves was as follows. There's a table of 14 numbers, almost all of which are positive, showing that the treatment was apparently beneficial. And one of them was negative, so that treated bit of field suffered some problem. You might get this sort of data written as a table, but it's quite likely you'll be given it as some sort of summarized value. So let's warn you about some things that you might need to know when you read these values. Well, you might get the sample values given to you as an algebraic term, small x, subscript I, where I is the index of the measurement from 1 up to capital N, or 14, the last measurement. You might see it written as equation 2.4b. You might have small x1, small x2, up to small xn, written as the set of numbers minus 57, the first one is a decrease, and the second one is 37, and all the others are positive numbers. You should be aware that when you're choosing to write reports, lowercase Latin characters like small x are used to represent actual observed values of data. So something that you have observed and written down, which is a number, like 15, that's a sample, and you'd write that down as, say, x subscript 4, your fourth observation. S might be the sample mean, simply the mean value of some observed quantities. That's small s. And these should be lowercase if they're actual observed values, because in statistics you'll find uppercase Latin characters like capital X1 refer to an as yet undetermined value, or something that you haven't yet measured but you're planning to measure. The reason for having small x or small Latin characters to describe numbers you have measured, and capital X or capital Latin characters to describe as yet unmeasured numbers that you will find out if you were to do the next experiment, say, is that if you need to write down the mathematical recipes for those things, they use different branches of maths. If I want to know, say, the sample mean of the measurements that I've got, I'd call that small x with a bar over the top. That's just an average of some numbers that I compute using arithmetic. If I wanted to write down, however, capital X with a bar over top, the sample mean of the as yet unknown values that I might observe, if I wanted to write that down with a mathematical recipe, I would need to write down something that depends on probability theory. So because that depends on a different kind of maths, we use small x for easy to work with values that we've measured, and capital X to remind us that we're dealing with as yet uncertain values, which we don't know what they're going to be. It could be a number of different things. We use Greek characters to describe population parameters. So these are parameters about which we might make an inference. So, for example, in the case of crop yields, small x to describe crop yield increase that we have measured, capital X to describe the next crop yield increase that we might measure, and we might use mu, Greek mu, to say, well, what is the, in average, in the whole world, what is the effectiveness of this treatment? And it's not just from the experiment I've done or more measurements that I've taken. What can I say generalizing about the effectiveness of this treatment as a property of the treatment itself? So you use Greek characters for when we're doing inferential statistics, and Latin characters for when you're using descriptive statistics. In particular, small Latin characters for the nice, easy descriptive statistics of here's my list of numbers. Great. A couple more things about reading algebraic notation of statistics, which you should know about maybe from a previous course, or you can read about if you need to understand it for interpreting textbooks and papers. You can read about it in the undergraduate course. You should know about some notation of sample mean and sample variance. So sample mean, if it's for, will be written S, small s if it's for measured values, capital S if it's for as yet unmeasured values. Sample variance is something you'll have to deal with sometimes, and you will also have an option of how to deal with this on your calculator. You should know, or you should be aware, that sample variance, which is often written s squared, small s squared, if it's for a description of, it's a descriptive statistic of some numerical values that you've got. It has two different forms, equation 2.4e and f. And these are actually different arithmetic formulae. One of them, s squared subscript capital N, and the other one, s squared subscript capital N minus 1. These are used for different things, and you should be aware of that if you need to interpret why algebra is done in a particular way. S squared subscript N, sometimes called the biased sample variance, although that's just a technical term, it's a description of the data that you've got. So you might use that if you had some set of data. X is the four measurements 90, 110, and another 90, and another 110. The sample mean would be x bar, small x bar, would be 100, and the biased sample variance, s squared subscript n, would be 100. That's because following equation 2.4e, you see that it's simply the average from the 1 over n term, the average squared difference between the measured values and the sample mean of the measured value is 100. The average difference between those is 10, or the average squared difference is 100. And that's what you get for s squared subscript capital N. And you would use that if you were describing some data itself sometimes. The reason why people and your calculators have access to an s squared subscript n minus 1, which is simply obtained as equation 2.4f, substituting in equation 2.4e your n for n minus 1, this comes up with a different value, as it happens for this data set, 133 and a third. And you might think, well, what on earth is the reason for this? Well, it turns out if you read in some depth the algebra of dealing with statistics, your s squared n minus 1, sometimes called the population variance, turns out to have a useful property, which is that your equation 2.4f provides you what's called an unbiased estimator of the population variance. As I said, what does unbiased mean? Well, what is its interpretation in statistics? Well, read the undergraduate course notes, because it's the sort of thing you can more effectively pick up from a page than you can from a spoken description. But the property is that when you have moderately sized data sets, like 4 or 5 measurements or 10 measurements, obviously there's very little difference between these. If you've got 100 measurements, and your difference between n and n minus 1 is the difference between 100 and 99. When you've got smallish data sets, it turns out that your bigger, more cautious number, your s squared subscript n minus 1, gives you a more accurate estimate of what the population variance is. Okay. So you should be aware of the fact that there are two different formulae for this, Mainly because when you use some software like MATLAB for data analysis, if you don't know, it actually makes a choice for you about which equation to use. And here's the choice it makes. You should know that if you give this very simple dataset or any list of numbers to MATLAB, you feed it X as a list of these 90, 110, and another 90 and another 110, you can tell it in the console to give you the mean of X, and it will, as you expect, come back with 100. You need to know that the default behavior for if you ask for variance of X is it uses equation 2.4f, and its default behavior for giving you the standard deviation of X is that it gives you the square root of equation 2.4f. If for some reason you want your data to be processed using the biased sample variance equation 2.4e and you're writing MATLAB code, that's something you need to know. You need to know to tell it to use the function in a different way. So be aware of that. I don't want to go through lots of properties of estimators in sampling theory statistics, but I do think you'll probably be using some MATLAB in this course, and you can, in this course or in the future, easily get into problems if you don't know how MATLAB handles variance, or what it thinks. It makes the choice of using one of the forms, and you need to know that there's multiple forms, simply for the descriptive statistic of what is the variance of my data. Good. What else should you absolutely know before you do a graduate data analysis course? You should know what a median of some list of numbers is. A median is defined as equation 2.4h, usually written the median of a sample of numbers that you know is written small x with a tilde over the top, swirly line, and you should know that the definition, slightly difficult to write down algebraically, is that the median of the sample is the middle value when it's put into order. Easy when the list of numbers has an odd number of entries, and when the list of numbers has an even number of entries, it's usually the halfway between the two middle values when they're put into order. Some properties of the median that I won't prove in this course. First of all, it's slow to calculate because in general it involves sorting a list of numbers. So computationally, if you can get away with using a mean average, that will often give you a program that's much faster. Another property of the median, though, a reason why you might want to use it even if it's slower, is because it's called something a robust estimator, or in plain English, because you're looking at the middle value from a list. If one of your values is weirdly wrong and takes on an extreme high value, that doesn't affect the median value, which stays where it was, whereas it causes problem for your mean value if you're using that as a description of your sample data. You almost certainly know all about means and medians, but again, you can read the algebra course if you particularly want to know more. What else do you need to know? Section 2.5, you should know what linear regression is in statistics, and you should know what a correlation coefficient is. Linear regression actually could mean a lot of different things depending on what subject you're talking about. So we could be precise, and we could talk about vertical linear least squares fitting, which is a more precise name. This is a method that's used usually to get you a descriptive statistic for some data that you probably have in a scatter plot already. So, vertical linear least squares fitting provides an answer to the question, what is the best fitting straight line through a scatter plot of points in 2 dimensions? Note that it's clearly not the only answer to this question, and you need to know about the hazards of the consequence of it not being the only way that you can draw a line. Anyway, the parameters of this straight line, so the gradient and the intercept, give you two numerical statistics to describe a sample of data that has two dimensions, or is on an XY scatter plot. A third numerical statistic of the sample is the correlation coefficient, which states the proportion of the variance of the y values, which is accounted for by the fitted straight line and the given x values. There is some maths for vertical linear least squares regression. Definitely, this is the sort of maths that you have to read from the notes if you want to learn about it. I'm absolutely not expecting you to memorize this, but this is the sort of thing that you would look up. If you don't like this derivation, I believe Wolfram MathWorld has an alternative derivation that is very good. There's also an appendix in this course lecture notes, which shows you we're trying to get the parameters, the intercept and slope for the line y equals a plus bx, which in some sense gives you the best fit to a cloud of data points. This is done using a straightforward recipe, and you end up with equations 2.5 d and e. You also, following through equations 2.5 f and g, you get equation 2.5 h, which gives you r squared. From that you get something called the correlation coefficient r between the sample of x values and the corresponding sample of y values on a scatter plot. So it follows that numerical recipe. The correlation coefficient r describes the fraction of the variance of the y values which is accounted for by the straight line fit. In practice, this r is said to describe the quality of the fit, but watch out. When you have a scatter plot of data or some measurements, you might generally it might, if it's simple data, it might be the sort which is well interpreted by a correlation coefficient, like the top row of this plot 2.5i. In the top row, you've got either some positive or negative trending data. If you have all of your data points lie on a perfect straight line, they lie exactly on this straight line and it has a positive slope, then your correlation coefficient is +1. If it's perfect straight line with a negative slope, a correlation coefficient of -1. If this is typical real data, and there's increasingly more randomness in the y value, but there's a positive trend, the correlation coefficient falls from 1 towards 0. And if there's a negative trend, but there's some randomness in the y values, then you have the less randomness in the y values, the closer the correlation coefficient is to -1. If you've got symmetrically random data, you have a correlation coefficient of 0. The reason I mention this is because there's a few awkward ways in which your correlation coefficient, which comes from equation 2.5h, can either be 0 or undefined. If the sample variance in either the x or the y data alone is 0, in other words, if you have a perfect horizontal line or also a perfect vertical line, then your correlation coefficient is undefined, because there's a divide by 0 in the equation. It's undefined, even though the data actually has a very simple behavior, which is that it is on a perfect straight line. It's just a perfect straight line that isn't well processed by trying to get a correlation coefficient from it. You can also have nasty data like the bottom row of figure 2.5i, in which there is some sort of trend in the data, but it's not described by a straight line fit. In general, your y values are either equally above the mean as below the mean, symmetrically as x changes. So there might be a sine wave behavior, but that looks like, as far as a linear fit is concerned, that looks like a flat horizontal line. So there can be the y value in some data can depend on x, but if the straight line has a 0 slope, then your linear correlation coefficient for the linear regression comes out as 0. That doesn't mean there's no dependence of y on x. It just means that a straight line with a particular slope doesn't give you a good description of it. Let's say one more thing about vertical linear least squares fitting, and that thing is that this recipe is used in large part because it's easy to apply, and also because it's relevant to many traditional kinds of experiments. Vertical linear least squares fitting corresponds on this slide to the left-hand picture. Essentially, we're trying to find the blue straight line which minimizes the sum of squares of those green residuals between the data points and the line. This is algebraically easy to do, and in traditional experiments you have x is a variable that you control exactly, so you know its true value, and y is some result which has some uncertainty or some natural variation in how it comes about. And so doing a fit which only bothers about uncertainty or error in the y direction, or minimizing those vertical offset residuals, is a sensible way to fit a straight line through your data. It's not the only way. There's an algebraically much harder way, which can involve just brute force, of you might want to do the right-hand figure of minimize the perpendicular offsets between your data points and your fitted straight line. That would be the kind of processing that you might need to do if you were doing measurements where you have both uncertainty in what you're measuring for x and uncertainty in what you're measuring for y. So, for example, if you have two imperfectly accurate measurement systems, each taking a measurement of the same thing, like the weight of a brick or something for a number of different bricks. The reason why in textbooks, especially in older textbooks, vertical linear least squares regression as the left-hand figure is used is largely because it's algebraically easy to do. So be warned about that. Right. Also be warned that the word regression can refer to a different phenomena from just fitting a straight line. We'll come back to that much later in the course when we talk about regression to the mean. Right, summary of some things that you should have got from this chapter on descriptive statistics. Well, in describing data, there's a balance between simplicity and detail. We mentioned the importance of making a suitable decision that gives you, when you present data, clarity, fidelity, and comprehensiveness. So clarity means simplicity. Fidelity means not accidentally missing out or forgetting to mention some important aspect of the data. So don't overgroup when there's a good reason not to, and don't forget to give detailed captions. And comprehensiveness, in other words, as well as your figure that you put in a report, generally you probably do want to make comprehensive numerical data available in a table in supporting material, probably on some open source archive these days. What else did we look at in descriptive statistics? Some of the important one-dimensional and two-dimensional graphs. We said something about numerical statistics, and I talked about one important case of when we have these descriptive statistics, the purpose is usually to draw some useful conclusion, but we looked at a hazard of overinterpretation in terms of the kidney cancer death rate in counties in the USA. In the next lecture, I'll come on to design of experiments, which is all about how we avoid the hazards of data analysis, how we avoid drawing bad conclusions, how we design experiments to, as much as possible, mean that we won't have to worry about making bad conclusions, or alternatively, worrying about hazards which will nonetheless be a risk when we do process some data. We'll see how to deal with, later in this course, Simpson's paradox, relatively easy, and regression to the mean, relatively hard, but both important phenomena. That's what's coming up.